Hello everyone, myself Bhanupriya BK, Assistant Professor, Department of Mathematics, MIT, Mysuru. In this video, I am going to explain Module 4, that is Ordinary Differential Equation of Higher Order, from the subject Mathematics 1 for Civil Stream with the subject code BMATC101. This module contains 4 concepts. First one, solution of higher order linear differential equation. Second one, method of variation of parameters, Cauchy's homogeneous differential equation, and last one, Legender's homogeneous differential equation. Let us start with some of the applications of the concept. Ordinary differential equations are used in many branches. A few applications are, it is used in earthquake technology, it is used in structural analysis, and it is used to find steady state fluid flow under the dams, and it is used to find deflection of beams while constructing the buildings. So, these are the few applications. So, let us start the concept. That is first one, solution of higher order linear differential equation. Here ODE of higher order. The equation of the form A naught nth derivative of y with respect to x plus A1 n minus 1th derivative of y with respect to x. Similarly, a n minus 1 first derivative of y with respect to x plus a n into y is equal to phi of x. Let us take this equation as equation number 1. So, this type of equation is called higher order linear differential equation. This equation can also be written as a naught d to the power n plus this is a1 d to the power of n minus 1, continuing like this, a n minus 1 d plus a n of y is equal to phi of x. Here this capital letter D is d by, that is derivative of a dependent variable with respect to the independent variable, which is called differential operator. This d is called differential operator here. So, this is the standard form of higher order linear differential equation. We can write this equation in this form also, in simplified form. And in the higher order linear differential equation, we have two types. One is homogeneous differential equation, another one is non-homogeneous differential equation. In equation number 1, I will represent this as equation number 2. In either of the equation, here the RHS function is function of x, that is phi of x. Homogeneous differential equation means if phi of x equal to 0. If phi of x equal to 0, then equation number 1 is called homogeneous differential equation. If phi of x is not equal to 0, then equation number 1 is called non-homogeneous differential equation. If this term equal to 0, then the equation is homogeneous. If this is not equal to 0, if this is a function of exponential term, trigonometric term, log term, or any functions, then it is called as a non-homogeneous function. Now, let us discuss the solution of homogeneous differential equation. And the solution of equation number 1, that is general linear order differential equation, contains the solution of the equation is y is equal to yc plus yp. Here yc is called complementary function and yp is called particular integral. We have the first term, yc is the solution of LHS part of the equation and yp is the solution of RHS part of the equation. So, yc is the complementary function that is obtained by the derivative part of the given equation, and particular integral is the solution of the RHS function. Whatever the function given, that depends on the nature of the function. By particular integral is the solution of the RHS part of the equation. Solution of equation number 1 is y is equal to yc plus yp, where yc is called complementary function, yp is called particular integral. As I already said, homogeneous differential equation means if phi of x equal to 0, then equation number 1 is called homogeneous differential equation. If phi of x is equal to 0, if this term equal to 0, then yp is also equal to 0. That is, in homogeneous equation, no need to find the value of particular integral since the phi of x value is 0. So, while solving homogeneous differential equation, just we need to find complementary function, no need to find the particular integral. While solving non-homogeneous equation, we have to find both the part, that is yc and yp, to find the complete solution of the given equation. So, let us start the solution of homogeneous differential equation. Solution of homogeneous differential equation. So, the RHS function is 0. So, this is a homogeneous differential equation, and that contains solution y is equal to yc, because here the value of particular integral is equal to 0 since the RHS function is 0. So, now how to solve the solution homogeneous differential equation? So, these are the procedure. First we have to write the given differential equation in differential operator form, that is a naught d to the power n plus a1 d to the power of n minus 1 and so on, a n minus 1 d plus a n of y equal to 0, where d represent differential operator here. So, we have to write the given equation in differential operator form. Next we have to write auxiliary equation. So, what is the meaning of auxiliary? Auxiliary mean represent a scalar or a constant term. We have to write the auxiliary equation from the given differential equation. For that, just we have to replace the d, that is differential operator, by a constant called m. I represent that constant as m. Then equation becomes a naught m power n a1 m power of n minus 1 plus a n minus 1 m plus a n is equal to 0. This is called auxiliary equation. So, depending upon the degree of the equation, the order of the equation, we get roots of that equation. So, after reducing the derivative d to m, we get an auxiliary equation which is in the form of a polynomial equation. If it is of degree 2, it is a quadratic equation, or it is more than 2, it may be a cubic equation or a polynomial equation. Depending on the degree, we get roots of the, here we have nth degree, then we get n roots of the equation. So, based on the obtained root, we get the complementary function. Based on the obtained root, we get complementary function. For that, we have three cases. In first case, if roots are real and distinct. If the roots are real and distinct. If the roots are real and distinct, for example, let us take m is equal to a comma b. So, here this is a general form, it is an nth order differential equation, that is a polynomial of degree n. While solving the problem, so this is the nth order differential equation, that is why it is a polynomial of degree n. So, in problem it may be of degree 2, degree 3, maximum it is of degree 4. That is why I will explain by taking two roots. So, let us take real and distinct roots as a and b. If a and b are the roots, then complementary function of the given equation is, based on the obtained root, we have to select complementary functions, okay, constant functions as complementary functions. Let us, since we have two roots, let us take c1 and c2. c1 into e to the power of first root plus c2 into e to the power of the second root. If the roots are real and distinct, the complementary function is c1 e to the power of ax and c2 e to the power of bx. Case 2, if the roots are real and coincident. Real and coincident means if the roots are real and same roots. In the first case we discussed real and distinct root, in the second case real and coincident or same root. Then the complementary function is, here also we have two roots, that means we have to select two complementary function, that is c1 and c2. But here c1 into e to the power of first root, C2 into e to the power of the second root. Here this x represent independent variable. So, in the given problem, first we have to write observe the which is dependent and independent variable. While writing the solution, we have to write the independent variable in terms of the dependent variable function, that is yc is equal to c1 e power ax, c2 e to the power of bx. So, if roots are real and coincident, that is a comma b, then the solution is in the form of c1 plus c2x into e to the power of ax. If two roots are coincident, c1 plus c2x into e to the power of ax. Suppose if we have one more coincident root, that is a comma a comma a, then we have to write the solution as c1 plus c2x plus c3x square into e to the power of ax. Suppose if we have one more same root, then c4 x cube e to the power of ax. This is the solution of real and coincident root, real and distinct root. And next, last one, case 3, if the roots are complex. If roots are complex, if we get a complex root means a roots in the form of a plus or minus ib. Here we have two roots, a plus ib and a minus ib are the two roots. Here also we have to select two complementary functions. A plus ib is the one root, a minus ib is the another root. Here while writing yc value, so here while writing yc value, a is the real part of the root, b is the imaginary part of the root. So, there we get e to the power of ax c1 cos imaginary root e to the power of real term into c1 cos bx plus c2 into sin bx is the solution of a complex root. So, there are totally three cases: real and distinct roots, real and coincident roots and a complex root. While writing solution of real and distinct root, based on the number of roots, we have to select complementary functions. As I written here, c1 e power ax, c2 e power of the second root bx. If the roots are same, that is real and same, c1 plus c2 into x e to the power of ax. While writing the complex root complementary function is equal to exponential term of the real term into c1 cos of imaginary element, that is bx, plus c2 sin of imaginary element bx. So, let us take some example based on these three cases. So, in the first case written here, roots are 1, 2 and 3. Then the value of yc is equal to, here 1, 2, 3 numbers are real numbers and distinct number. So, that is why roots are, we have to select three complementary function, c1 e to the power of 1x plus c2 e to the power of 2x plus c3 e to the power of 3x if real and distinct root. We will take one more example, m is equal to 2, 2, 3. Here also we have 3 roots, while 2 are real and coincident and 1 is the distinct root. Since we have 3 roots, we have to select 3 complementary elements. Yc is equal to, for this real and coincident root, we have to take case 2 result, that is c1 plus c2x into e to the power of 2x. This is for real and coincident root. And last distinct root c3 e to the power of cx. Next, for complex root, 2 plus or minus 4i as one root, comma I. Here we have 3 roots. One root is 2 plus 4i, one root is 2 plus 4i, another one is 2 minus 4i, I will take this as 1, another one is 2 minus 4i, and the last root is the real root. For this, we have to combine the solution of case 1 and case 3. In case 1 we have to take real and distinct, in case 3 we have to select complex root. So, by writing solution for this, yc is equal to, for the obtained complex root, e to the power of real part of the root. What is the real part here? 2. E power of 2x into c1 into cos imaginary part, that is 4, cos 4x plus c2 into sin 4x is the imaginary root, plus the last one for this real root, c3 is the next complementary element into e to the power of 1x. So, these are the examples of different roots of the given differential equation. Let us solve some problems on this. Let us solve first problem on homogeneous differential equation, that is d square y by dx square plus 3 times of dy by dx plus 2 times of y equal to 0, and this is a second order differential homogeneous differential equation since we have RHS function as 0. So, while solving the problem, so as I already explained, what are the procedure? First step, we have to write the given equation in the differential operator form, then we have to write its auxiliary equation, then we have to find the roots of the equation. Based on the obtained root, we have to write the solution of complementary function. So, let write the given differential equation in the differential operator form. Differential operator d is equal to d by dx here. So, what we have in the first one? Second order derivative. That means here the coefficient is 1 into d square plus 3 times of first order derivative. D by dx is d plus 2 times of y equal to 0. So, the differential operator equation. Next, we have to write auxiliary equation of the same. Auxiliary equation means we have to replace the differential operator d by m. Auxiliary means a constant term. So, then auxiliary equation is m square plus 3m plus 2 equal to 0. Here the degree of the equation is 2. That means it is a quadratic equation. If it is quadratic equation, we can simply solve by using factorization. So, here the values are 1m squared, 3m plus 2. We can solve in two ways, one by using factorization or you can solve directly by calculator. If it is of degree 2, we can use factorization. If it is more than that, we have to use the method of synthetic division. So, in the next problem I will explain that. So, here since it is a quadratic equation, factorize this m squared, here 3m and 2 we have, hence the factors are 2m plus 1m plus 2 is equal to 0. 2 plus 1, 3m, 2 into 1 is equal to 2. So, now again simplifying this, in the first two element common term is m, on taking m as common element, the remaining element is m plus 2. Here nothing is common, that is why I will write 1 as common term. 1 into m plus 2 is equal to 0. Again the common element is m plus 2 into m plus 1 equal to 0. Equating each term equal to 0, m plus 2 equal to 0, m plus 1 equal to 0. Therefore, m is equal to minus 2, m is equal to minus 1. Therefore, roots of the given equation is minus 1, minus 2, which are real and distinct root. Therefore, solution is, since the given differential equation is a homogeneous one, here particular integral or yp value is 0, therefore, y is equal to, yc is the solution. What is yc here? Y is equal to, we have real and distinct root, that is we have to take the solution of case 1. For two roots, we have to select two complementary elements, that is c1 e to the power of the first root plus c2 e to the power of the second root. So, this is the solution of the given differential equation. First we have to write the equation in differential operator form, then we have to write auxiliary equation, then we have to find the roots of the equation by using whether by factorization or synthetic division or using calculator we can find the roots. -1, -2 are the obtained roots here. Based on the obtained roots we have to write the solution of complementary function. Since yp is equal to 0, y is equal to c1 e power of minus x plus c2 e power of minus 2x is the solution of given equation. Let us take one more problem. Second problem is d cube y by dx cube plus 6 into d square y by dx square plus 11 dy by dx plus 6y equal to 0. This is also a homogeneous differential equation with order 3. So now first write the given differential equation in differential operator form, that is let d cube plus 6d square plus 11d plus 6 of y is equal to 0. So this is the differential operator equation. Next we have to write auxiliary equation of this. Auxiliary equation is m cube plus 6m square plus 11m plus 6 equal to 0. So after writing the auxiliary equation we have to find the roots of the equation. In the previous problem it is a quadratic equation, by factorization we get roots. Here it is a cubic equation, factorization is not possible here, that is why by the method of synthetic division we have to reduce this one to quadratic equation. If the given equation is of degree 4, by applying synthetic division we have to reduce that to degree 3. Again using the same synthetic division method we have to reduce that to quadratic equation. To find the roots of this, since it is of degree 3 we get 3 roots here. We have m cube here, we get 3 roots. To find the 3 roots we have to apply the method of synthetic division. Before applying synthetic division method, first we have to find one of the roots of the equation. First we have to find one of the root of the equation by the method of inspection. By substituting values for this equation, we have to find one of the root. After getting that one root, using that one root we have to divide the coefficient of this, that is the method of synthetic division, to get the quadratic equation. So by the inspection method let us find one root of the equation. If let us start from 0, if m is equal to 0 we get 0, 0, 0. If m is equal to 0, 0 plus 0 plus 0 plus 6 which is not equal to 0. That means 0 is not a root of this equation. Next, if m is equal to 1. So, but in the given equation all the coefficients contains positive sign, plus 1, plus 6, plus 11, plus 6. That means on substituting any positive value we get a number greater than 6. For this 6 we are adding 1 times of 11, 1 time of 6, 1 time of 1, or if we substitute m is equal to 2 we get more than that. That means on substituting positive value we did not get root here, because the m value is a root if the equation is 0 equal to 0. But on substituting positive value we get we get a value greater than 6. So that is why let us try negative values. Substitute m is equal to minus 1. On substituting m is equal to minus 1 you get minus 1 whole cube, that is minus 1, plus 6 into minus 1, 6 into minus 1 whole square, that is plus 1, 11 into minus 1 plus 6 equal to 0. So here we get a minus 1 plus 6 minus 1 plus 6 minus 11 plus 6 equal to 0. 6 plus 6 is 12, minus 11 minus 1 is 12, 12 minus 12 is equal to 0. Therefore, m is equal to minus 1 is the one of the root. So now we have to divide the coefficient of this cubic equation by minus 1 to reduce this equation to a quadratic equation. So let us apply the synthetic division method. Coefficient of the given equations are, write in the decreasing order, m cube, m square, m, and last one a constant term. So now coefficient of m cube is 1, coefficient of m square is 6, coefficient of m is 11, coefficient of a constant term is 6. Now we have to divide that by obtain one of the root. So divide that values by minus 1. On dividing, the last remainder must be equal to 0. Then minus 1 is the correct root of the given equation. Last root must be equal to 0. Then we get a quadratic equation. So to divide this, let us take the first term as 0. So we have to add or subtract the obtained values depending on the sign of the number. 1 plus 0, 1. Then we have to multiply here, 1 into minus 1, we get minus 1. 6 minus 1, that is equal to 5. Minus 1 into 5, we get minus 5. 11 minus 5, that is 6. Minus 1 into 6, that is minus 6, and 6 minus 6 is equal to 0. This value must be equal to 0. Then an equation with 4 coefficient reduced to an equation with the 3 coefficient. That means one value decreases here. So now write the equation in the remaining form. Constant term power 1 power 2. So what we get here, 1 into m square plus 5 into m plus 1m square plus 5m plus 6 is the constant term equal to 0. So this is the obtained quadratic equation. So let us write that m square plus 5m plus 6 equal to 0. We can solve this by factorization, applying factorization method. Here we have 5m, here we have 6. So the coefficients are 2 and 3. 2 plus 3, 5m, 2 into 3, 6. So what we get? 2m plus 3m plus 6 equal to 0. On taking m as common term, we get m plus 2. On taking 3 as common term, we get m plus 2. On taking m plus 2 as common term, we get m plus 2 and m plus 3 equal to 0. So then two factors are m plus 2 equal to 0, m plus 3 equal to 0. After that I will continue here. M plus 2 equal to 0, m plus 3 equal to 0. That means m is equal to minus 2 and m is equal to minus 3. So therefore the three roots of the given equation is minus 1, minus 2 and minus 3. So therefore the roots are minus 1, minus 2 and minus 3, and these obtained roots are real numbers and also a distinct roots here, minus 1, minus 2 and minus 3. The obtained roots are real and distinct roots. Therefore solution of the given differential equation is y is equal to yc, y is equal to, for the distinct root we have to take case 1 solution, that is c1 e to the power of first root plus c2 e to the power of the second root plus c3 e to the power of the last root. c1 e power of minus x, c2 e power of minus 2x, c3 e power of minus c3 to the power of minus 3x is the solution of the given differential equation. Let us solve one more problem on homogeneous differential equation, that is d power of 4 plus 64 of y is equal to 0. Here this is an equation of fourth order. So let us find the roots of the given equation. Since it is of order 4, we have to find 4 roots of this. For that, first find the auxiliary equation. So here given that d power of 4 plus 64 of y equal to 0. It is a homogeneous equation since phi of x is equal to 0. That means we need to find yc only. And the auxiliary equation is m to the power of 4 plus 64 is equal to 0. To find the 4 roots of this equation, we have m power of 4 plus 64 equal to 0. We have only 2 elements here. That means we can't apply factorization to find the roots. To apply synthetic division method, observe the equation, we have m to the power of 4. To apply synthetic division method, by inspection, first we have to find the one root of this equation. By inspection, we have to find one root of this equation. After that, by using that one root, we have to apply the method of synthetic division. But observe here, for this m, we have even number as a power. M contains even power, that is 4. On substituting any negative value or positive value, it is greater than 64. If m is equal to 0, we get 64. If we substitute any positive value, it is greater than 64. On substituting any negative value, we get minus 1 to the power of 4. It will be a positive. That means again it is greater than 64. So we can't apply inspection method also. For that, I am writing this equation to write in the standard form. So this can be written as, we have m to the power of 4 here. So this can be written as m square whole square. Since factorization is not possible and synthetic division is not possible, try to apply standard result on this equation to find the roots. M square whole square plus 64 can be written as 8 square equal to 0. Now this in the form of a square plus b square, where a is equal to m square, b is equal to 8. This is in the form of a square plus b square. Hence from the result, a plus b whole square is equal to a square plus b square plus 2ab. From this, the value of a square plus b square, that is a square plus b square is equal to, we have a plus b whole square, shifting this one element, a plus b whole square minus 2ab. The value of a square plus b square equal to a plus b whole square minus 2ab. In this problem, the value of a is equal to m square, b is equal to 8. So this can be written as, applying that result, m square plus 8 whole square minus 2 times of m square into 8 is equal to 0. So applying standard result, a plus b whole square in altered form, that is a square plus b square equal to a plus b whole square minus 2ab. So now simplifying this, we get m square plus 8 whole square minus, we get m square plus 8 whole square, this is one term, minus, simplifying this again, 2 into 8 we get 16, m square equal to 0. Again simplifying this equation, this can be written as m square plus 8 whole square minus 16 can be written as 4 square. 4 square into m square, that can be written as 4m whole square is equal to 0. Again the obtained result is also in the standard form, a square minus b square. So this is the first result we are using, and the second result is a square minus b square equal to a plus b into a minus b. The value of a square minus b square equal to a plus b into a minus b. A square minus b square is equal to a plus b into a minus b. So I am writing this obtained result in the factors form by applying this result, where a is equal to m square plus 8 and b is equal to 4m. Substituting, we get m square plus 8, a square minus b square equal to a plus b into m square plus 8a minus b whole square is equal to 0. Here we have two factors. Splitting the two factors, we get the first factor m square plus 4m plus 8 equal to 0. M square minus 4m plus 8 equal to 0. M square plus 4m plus 8 equal to 0. M square minus 4m plus 8 equal to 0. So now we need to simplify this. To simplify this, first observe if it is possible to factorize this equation. Otherwise, applying the formula we have to solve. So here we have 4 and 8. So we can't find any factor satisfying these values. So hence applying the result, here A is equal to 1, B is equal to 4, C is equal to 8. Here A is equal to 1, B is equal to -4, C is equal to 8. So formula is M is equal to minus B plus or minus square root of B square minus 4AC divided by 2A. That is for both the equation. Substitute the value as A, B, C in each of the equation to find the roots of the given equation. We get 4 roots here. 2 roots from the first equation, 2 roots from the second equation. So let us find the roots of these equations. To find the roots of the equation, m square plus 4m plus 8 equal to 0, m square minus 4m plus 8 is equal to 0. Here A is equal to 1, B 4, C 8. A1, B minus 4, C 8. Substituting the result in the first equation, minus 4, B is equal to 4, minus 4 plus or minus square root of 4 square is 16 minus 4 into A value is 1, 4 into 1 into C value is 8 whole divided by 2 times of A, 2 times of 1. In the second equation, M is equal to, here the value of B is minus 4, minus of minus 4 is plus 4 plus or minus square root of 16 minus 4 into 1 into 8 whole divided by 2 times of 1. Simplifying this again, M is equal to minus 4 plus or minus 16 minus 4 into 8. Minus 4 into 8 is minus 32. 16 minus 32 is minus 16 divided by 2. In the second equation, 4 plus or minus, again 16 minus 32 is minus 16 divided by 2. Simplifying again, M is equal to minus 4 plus or minus the value of root 16. 16 is a perfect square. The value of root 16 is 4, and since we have minus sign, the root of minus 1 is an imaginary term. Minus 4 plus or minus I into 4 divided by 2. Similarly, M is equal to 4 plus or minus 4I divided by 2. Again, root of minus 16 is 4I. Simplifying this again, and 4 and 4 we have, by dividing by 2, we get M is equal to minus 2 plus or minus 2I. The first two roots are minus 2 plus 2I, minus 2 minus 2I, and the next M is equal to 2 plus or minus 2I. So therefore, the complete roots of the given equation are, the roots are minus 2 plus or minus 2I, 2 plus or minus 2I. So totally we have 4 roots, minus 2 plus 2I, minus 2 minus 2I, 2 plus 2I, 2 minus 2I, and the obtained roots are complex roots. That means it comes under case 3. If the roots are complex, then we have complementary solution. As based on these 4 roots, we have to select complementary elements, that is C1, C2, C3, C4. For that, here we have the real term is minus 2 for the first root, hence e to the power of minus 2x into C1 cos 2x plus C2 sin 2x. For the first root, e power of real term, e power of minus 2x into C1 cos 2x plus C2 sin 2x, plus for the next two root, that is e to the power of 2x, e to the power of the real term into C1 C2 completed here, hence C3 cos 2x plus C4 into sin 2x. So therefore, the complete solution of the given equation is y is equal to yc. Since the RHS function is 0, the value of yp is 0 for homogeneous differential equation. Therefore, y is equal to e power of minus 2x c1 cos 2x plus c2 sin 2x plus e to the power of 2x c3 cos 2x plus c4 into sin 2x. So this is the solution of the given differential equation d power of 4 plus 64 of y is equal to 0. If it is not possible to factorize, or if it is not possible to apply synthetic division method, then we have to use standard result to simplify the given equation.